So in problem 1 here, we want to use the cancellation laws to simplify this expression. So remember that exponents, inside exponents on logs, can factor up and down. So we can take that -3 and put it as an exponent over the 5. So this is e to the natural log of 5 to the -3 power. And then cancellation law, e and ln cancel each other, so we just get 5 to the -3, which is 1 over 5 cubed, or 1 over 125. So you want to try and rearrange your expression in the homework so that you've got the e and the log right next to each other and you don't have a number out in front of the log. Then they can cancel each other out. Next up, we are solving a log equation and an exponential equation. For the log equation, you undo natural log with exponential, natural exponential, so e to the natural log of 3x plus 1 will equal e squared. And then exponential natural log cancel, so we just get 3x plus 1 is e squared. And e squared, that's just a number, so now we'll solve for x. So subtract 1 on both sides. 3x will be e squared minus 1. And then divide by 3 on both sides. So your x is going to be e squared minus 1 over 3. For the exponential, we want to do logs on both sides. So natural log of e to the 2 plus 3x will equal natural log of 6. And then natural log and exponential cancel each other. We've just got 2 plus 3x is equal to log of 6. And now this is a regular equation. We can solve for x. So subtract 2 on both sides. 3x will be natural log of 6 minus 2. And then divide both sides by 3. So x is going to be your natural log 6 minus 2 and all over 3. So undo logs with exponentials, undo exponentials with logs. Next, we are computing a limit here, and we've got a bunch of exponentials in here. And what you want to notice is when you've got e to a big negative power, when x is approaching infinity, that is going to approach 0. So this piece approaches 0, and so does this piece here. But then this piece is going to approach infinity, and this piece is also going to approach infinity. So this thing is of the form infinity over infinity, which is indeterminate. So we need to do some algebra work here to change the form so that this is determinate. So what we want to do is we want to take and multiply here the top and bottom by e to the negative 5x. And that's going to make these e to the 5x powers go to 0. So multiply top by e to the negative 5x. So we want all negative exponents here. And the bottom also by e to the negative 5x. We've multiplied top and bottom by the same thing, so that doesn't change the algebraic value of this expression. It's algebraically equivalent. We want to multiply those negative exponentials in, distribute them in. So e to the negative 5x times e to the negative 5x. When you multiply, you add exponents, right? So that's going to be e to the negative 10x. So negative 5x and another negative 5x. And then do the same thing here, minus 2 e to the 5x plus negative 5x. That's e to the 0, which is 1, so this is just 2. And then in the denominator, same thing, e to the negative 5x comes in here. We will have a 3e to the negative 10x, adding exponents. And then when you multiply these guys together, add exponents, that's e to the 0, which is 1. So now these two pieces here are approaching 0. But then these are at -2 and +1, so this just looks like 0 minus 2 over 0 plus 1, which is -2. So now we've got an actual number. It's no longer that indeterminate form. So you want to multiply top and bottom on your problem by a negative power. So next up, we want to differentiate e to a function. And remember, when you differentiate e to a function, so e to the f of x, and we're doing the prime of that you get back e to the f of x, and then times the derivative of the inside function, so times f prime of x. That's chain rule. So we differentiate this guy, our y prime, then is going to be e to the function t sine 2t, and then times the derivative of this smaller inside function, so times derivative with respect to t of t sine 2t. Now that's a product of two functions, so we got to use a product rule here. So let's call this f, and the sine 2t will be our g. So this part's going to stay the same, so e to the t sine 2t. And now derivative of the inside, we want to do a product rule, f prime g plus fg prime. So f prime, the derivative of t is 1 times our g, sine 2t, plus our f is t, and then our g prime, derivative sine 2t is going to be cosine 2t, but then times 2 times the derivative of the inside, because it's not just cosine t, it's cosine 2t, it's cosine of a function. So times 2. And there's our derivative, not simplified, but we've got our derivative. We can simplify a little bit here. So t sine 2t is our exponent, and then 1 times sine 2t is sine 2t. And then plus 2 times t, we can bring the 2 out in front. 2t cosine 2t. And so that's a simplified derivative. So you want to do something similar here. When you're differentiating an exponential function, you may have to use a chain rule, may have to use a product rule or a power rule to get your derivative of the inside. Next up, we're trying an integral here. I see a function 2t to the 4th, and then its derivative would be 8t cubed, and we've got the t cubed there. So we can use a u substitution here. Let u equal 2t to the 4. And so our du will be the derivative, 8t cubed, and then times dt. Well, we've got the t cubed dt. So let's take our t cubed. That's e to the 2t to the 4. And I am going to multiply by what I need, 8, and then compensate. Multiplying by 1/8. So haven't changed the value of the expression. So then these two pieces make up our du. And then here's our u. So this will just be 1/8. And then integral of e to the u. And then these two pieces make up our du. And the antiderivative of e to the u is e to the u. It's its own derivative and antiderivative. So this is 1/8 e to the u, and then plus a constant, because this is an indefinite integral. And then we just need to plug back in our u. So this will be 1/8 e to the 2t to the 4th, and plus a constant, and we've got it. So you see a function and its derivative, let u equal the function. So here we have another integration example. We're trying to integrate e to the x over 2 plus e to the x quantity cubed. So again, I see a function and its derivative. The derivative of 2 plus e to the x will just be e to the x. So let's use a u substitution again here. U equals 2 plus e to the x. So then my du will be derivative of 2 is 0. Derivative of e to the x is e to the x, and then times dx. So here's my du up on top. And then this is u down here. So this will just be integral du over u, and that gets cubed. So over u cubed. So we can bring that u cubed up to the top as a negative exponent, so u to the negative 3 du. And now to integrate that, we raise the exponent, divide by the new exponent. So u to the negative 2, divide by negative 2, and plus a constant because this is indefinite. So we can bring that u to the negative 2 downstairs as a positive 2 exponent. So this will be negative 1 over 2 u squared. I took the negative and brought it out in front, plus a constant. And then we just have to plug back in our u. So this will be negative 1 over 2, and then times the quantity 2 plus e to the x. That guy gets squared, and plus a constant, and we've got it. And then this last example, little bit of work here. We have a function x squared e to the 2x. We're finding intervals of increase and decrease. So remember, when you're finding intervals of increase and decrease, you find your first derivative and then you do a sign test on it. So we need our f prime here. So for a, our f prime of x is going to be, and we're going to have to do a product rule here, right? Here's our f, here's our g. So we want f prime, which is 2x, times our g, e to the 2x, plus f, x squared, times g prime. So that's e to a function. You differentiate e to a function, you get e to the function, 2x, times derivative of the inside, so times 2. So there's our f prime. We want to find out where this is equal 0, so we want to set it equal 0 and solve. Before we do that, notice we've got a common factor here of 2x, and here we've got a 2 and an x in there, and then also the e to the 2x. So we can pull out here a 2x, e to the 2x is our common factor, times, we factor everything out here, there's just a 1 left, and everything comes out here except one of the x's, so plus x. And set that guy equal 0, because that's how you find critical values. And so if this piece is equal 0, so 2x e to the 2x equals 0, well, exponentials are never 0. E to a power is never 0, so that means 2x had to equal 0, which means x equals 0. Or the 1 plus x could be equal 0. So you set each factor equals 0. Bring the 1 over as a negative, x equals negative 1. So there's our critical values. And then to do increase, decrease, remember you do a Sine chart here. So we will mark off our critical values of negative 1 and 0. And then we want to analyze the sign of f prime above and then tell what f is doing below. So pick a test value in each region here. So I'm going to test negative 2 in my derivative, negative 0.5, and then positive 1. So if I plug negative 2 in here into my f prime, this piece will be 2 times negative 2, that's negative. E to the 2x is always positive. So negative times positive, that's a negative. And then plug the negative 2 in here. 1 plus negative 2, that's negative. So negative times negative, that's going to equal a positive. So f is increasing on that interval. Plug in a negative 0.5. Again, 2 times negative 0.5 is negative, times a positive e to the 2x. That's going to be negative. 1 plus negative 0.5, that's going to be positive 0.5. So negative times positive is negative. So the function is decreasing in that interval. And then plug a positive 1 in here. 2 times 1 times e to the 2 times 1, that's positive. 1 plus 1, that's positive. So this is positive times positive, which is positive, and your function's increasing. So your increasing intervals, are going to be negative infinity up to -1. So that's this piece here. And then also 0 to infinity. And remember, you include the endpoints. And then it'll be decreasing on this interval here, -1 to 0. So that's our first derivative. Intervals of concavity, so that's concave up, concave down. So that is going to be second derivative. So let's take this piece here for our f prime, and then we want to do a product rule on that. So our f prime of x will take 2x e to the 2x times 1 plus x. So now we need our f double prime. So again, let's let this be our f, and then this will be our g. So we want to do f prime g plus fg prime. So f prime, well, that's going to be a product rule. Okay, so derivative of the first piece, 2, times the second piece, e to the 2x, plus the first function, 2x, times derivative of the second function, e to the 2x times 2. So that's our f prime, derivative of the first, times the second piece, 1 plus x, plus the first function, 2x e to the 2x, times the derivative of the second function, which is just 1. So let's go ahead and simplify here. So inside the parentheses here, we've got a 2 e to the 2x plus 2 times 2x, 4x e to the 2x. And that's multiplied by 1 plus x. And then we've got a 2x e to the 2x on the end. So let's see, we want to take our 1 and multiply it by each one of these guys. And then do the same thing with our x. Multiply that by each one of these. So we're going to FOIL that out, basically. So, so our first terms here, 2 e to the 2x. Our outer terms, x times 2 e to the 2x, so that'll be 2x e to the 2x. Our inner terms, 1 times 4x e to the 2x will be 4x e to the 2x. And then our last terms, we'll have an x times that x, this will be 4x squared e to the 2x. And then we still got this 2x e to the 2x on the end. Okay, so now we want to collect our like terms here. So we've got e to the 2x there. That's the only e to the 2x term. So 2 e to the 2x. And then this is a 2x e to the 2x, a 4x e to the 2x, and another 2x e to the 2x. So you're going to add your x terms. So 2x and 4x is 6x, and another 2x is 8x. So plus 8x e to the 2x. And then the last one is that 4x squared, plus 4x squared e to the 2x. And then we want to set this equal to 0 and solve. Before we set it equals 0, let's factor like we did up above. We've got a common factor of 2 that we can pull out. And then we've got a common e to the 2x that we can pull out. And what's left here is a 1 plus what's left here. We took a 2 out, took the e to the 2x out, so a 4x. And then here, took out the e to the 2x, and then a 2, so 2x squared left. So that's our factored form, and then we set that equals 0. Well, this piece can never be equal 0. This is always greater than 0. So that means that we want to set this equal 0. So let me bring the 2x squared out in front. So 2x squared plus 4x plus 1 is equal to 0. And then we want to factor that and set each factor equals 0, similar to what we did up here with the first derivative. Now, it turns out that this does not factor, and that's just the example that I made up. Yours, I believe, will factor in the problem that you have to do. But ours, we have to use the quadratic formula. So remember, x is negative b plus or minus square root b squared minus 4ac all over 2a. So our a is 2, our b is 4, and our c is 1. So negative b will be negative 4 plus or minus square root. B squared is 4 squared minus 4 times a is 2 times c is 1. And then all over 2a, so 2 times 2. So this will be, let me take that down here, negative 4 plus or minus b squared, that's going to be square root of 16 minus 8 is 8. So this will actually be square root of 8. And then all over 4. So we can split this apart here and do negative 4 over 4 plus or minus root 8 over 4. And that root 8 I'm going to break up as root 4 times 2. And then we can do square root 4 square root 2. So this will be 4 over 4 is just 1, negative 1, plus or minus. Root 4 is 2, and then we still got the root 2 inside the square root, and then over 4. And then this 2 will cancel in here, so we get a negative 1 plus or minus root 2 over 2. So those are our two cutoffs for f double prime, and we want to test concave up, concave down. So we want to go ahead and do a sine chart here like we did up above. So we've got our negative 1 minus root 2 over 2, and then negative 1 plus root 2 over 2. And we're going to pick test number in each region. And we're going to tell about f double prime above there, and then what f is doing below the number line. So let's give ourselves a little bit more room here. Okay, so for test numbers, well, negative 1, root 2 over 2 is about 0.7. So this is negative 1.7. So we could pick negative 2. In between these guys, we could just pick negative 1 plus 0.7 is about negative 0.3 approximately. So we could pick a negative 1 there, and then we could pick a 0 over here. And we're going to substitute those in right here into our f double prime. So if you plug a negative 2 in, well, e to any power is always positive. This piece is always positive, so we just need that piece there. So we would have 1, 4 times negative 2, negative 8. And then 2 times negative 2 squared. Negative 2 squared is 4, so that's a positive 8. So we have 1 minus 8 plus 8 is 1, so that is positive. So we are concave up. Plug in a negative 1. This piece is positive. This will be a negative 4. This will be a positive 2. So 1 minus 4 is negative 3 plus 2, negative 1. So that's negative. Concave down. Plug in a 0, 1 plus 0 plus 0, that's positive. This is concave up. So we are concave up on negative infinity to negative 1 minus root 2 over 2. And then remember with concavity, you don't include the endpoints. And then union, negative 1 plus root 2 over 2. Up to infinity. So that's this interval and this one. And then we are concave down on the interval in the middle. So negative 1 minus root 2 over 2 to negative 1 plus root 2 over 2. And then they want to know, do we have any points of inflection here for part C? So that's part B, got our concavity. And then part C, we are going to have 2 points of inflection because it changes from concave up here to concave down here, and then concave down back to concave up. So these are both x-coordinates of inflection. So our points of inflection here are going to be negative 1 minus root 2 over 2. And then the y value, you'll just take that and plug it into the original function. F plug in negative 1 minus root 2 over 2. And then same thing with the plus. So we'll have negative 1 plus root 2 over 2. And then your y-coordinate, you're going to plug back into the original function. So f of negative 1 plus root 2 over 2. And then our original function, remember, is x squared e to the 2x right here. So that's what we're plugging into to get our y-coordinates. So these inflection points are kind of messy here. We've got our x-coordinate is negative 1 minus root 2 over 2. And then our y-coordinate, we're going to take that, plug it into the function, so that gets squared. So negative 1 minus root 2 over 2 squared. That's the x squared part. Remember f of x here. Just remember f of x is x squared e to the 2x. So there's the x squared part, and then e to the 2 times negative 1 minus root 2 over 2. So that's our y-coordinate there. And then same thing here, but with a plus sign. So negative 1 plus root 2 over 2. And then negative 1 plus root 2 over 2 squared. And then times e to the 2 times negative 1 plus root 2 over 2. So there's our inflection points. And we could work out decimals for this if we wanted to. So this is, I'm sure that this is messier than the example that they have you work on, but it should use the same types of ideas. So good review here from Calc 1, increase, decrease, concave up, concave down, and inflection points.